One day you trip over a rock while carrying a part of your church's stained glass mosaic. A part of the stained glass mosaic breaks off and shatters. You need to find the length of the sides to get a replacement piece. You find the blueprints of the church's stained glass window to see if you can find the measurements for the broken piece's size lengths. However, the length of the side is faded, so you can't tell what it was. How can you find the length of the final side of the fragment? You have no measuring tools, but you have measurements of all the other fragment sides. If the pastor finds out, you will be excommunicated. What could you do? You faintly remember that time in Homestead Math Club where the officers were teaching a theorem about the proportionality between sides of a triangle. If only you could remember.
Say that we have triangle ABC and we draw a line from each vertex to the opposite side and have each of those lines intersect at one point. Let's label the middle intersection point P and the intersections with each of the sides B, E, and F. Now let's take a look at specifically triangle CPE with height H. We can write the area for this triangle as 1/2 BH, which is the same as 1/2 CE times H. Now let's take a look at triangle BPE, also with height H. The triangle will also have its area as 1/2 BH, but instead of B, the base is EB. This gives us the equation for the area of the triangle as 1/2 EBH. Now that we have both of these equations, we can make a ratio between them and get that the area of CPE over BPE is equal to 1/2 CEH over 1/2 EBH. We can further simplify this ratio by canceling the 1/2s and the h's. Get that CPE over BPE is equal to CE over EB. Increase the length of H and take a look at triangle CAE with the area 1/2 BH, which is 1/2 CEH. Also the triangle BAE, which has an area of 1/2 BH, which is 1/2 EBH. If we make a ratio between the areas of the triangles CAE and BAE, the 1/2s and heights can be cancelled out, and what's left is the ratio between the two triangles to the two bases. Triangle CAE over BAE is equal to CE over EB.
We now have two area ratios with two sets of triangles. However, triangle CAE contains two smaller triangles, CPA and CPE. The sum of the two areas of CPA and CPE gives us the area of CAE. So the difference between the areas of CAE and CPE results in the area of CPA. Using the ratios we had earlier, we can multiply the area BAE to CE over EB, which isolates CAE, and we can also multiply the area BPE to CE over EB, which isolates CPE. Since we isolated CAE and CPE, they can be substituted into the equation involving the sum of the triangles as shown. The ratio CE over EB is factored out, and when the area of BPE is subtracted from the area of the triangle BAE, the resulting triangle BPA is formed. BPA can be substituted for the difference in the two areas BAE and BPE in the sum equation, and then multiplied on both sides to get the resulting equation, areas CPA and BPA equal to lengths CE over EB. We can apply this property for every other side as a base. You get these three ratios, and you can see that if you multiply all of the triangle area ratios together, it all cancels out and it equals 1. If we substitute all of the triangle area ratios with the base ratios, then you get Ceva's theorem. You can further simplify this and see that the product of every other part of a side is equal to the product of the latter sides.
You can see from the stained glass triangle that it is formatted just like the triangle from Math Club. Just plug in the values of all the sides you have and then isolate your unknown side. Then you have your answer.